Hey guys, my name is Adrienne and welcome to Organic Chemistry 2, part 6 of these recorded sessions. So today we'll be going over for most of y'all chapter 18 and in general electrophilic aromatic substitution. So a lot of these chapters coming up, dealing with aromaticity and conjugation, things like that. Last chapter we just talked about conjugation, resonance. So now we're kind of moving it a bit further with the reactions, right? And again, first things first, we'll be doing our review first. So feel free to you know answer along or follow along. But if you just want to take screenshots or save the test review, or not the test review, but the chapter review, and do them on your own, then come back. Feel free to do that. So a lot of different ways you can approach this, and at the end we'll have a little summary of what are the main takeaways. So if you want to compare notes, I'll have my notes for you guys, and then we'll discuss, right? And also, this is one of the prime examples of why we're doing practices first, because these are all reactions, and other than a couple of memorizing things like that, you either know it or you don't, right? So this is why we're doing this, and this is why you know it makes it more smoother, and it's kind of getting to the point quicker type thing. And again, it's not a lot of concepts because reactions are, if you're familiar with them, you're good with them, right? So it's not really like very tricky or anything like that. It's just like knowing the reactions itself, and also we'll be talking about later about the groups, some of the groups we'll be working with. So things like that. And again, we've up to this point chapter 18, right? We've learned our basics. We've learned pretty much the general, pretty much everything we need to, you know, everything we need to use or our resources to kind of maneuver with these questions. We know all the reaction types, right? Addition, substitution, things like that. So, and we know what conjugation is, resonance is. So now we're just kind of combining everything, and everything is the same. Steric hindrance plays a part. Electronegativity plays a part. So you're probably hearing your professors right about now. Everything's getting repetitive. So, um, which is always good because less study time for you guys, right? Hopefully. And yep. With that being said, let's get started with the review. So again, this reviews, each review contains 20 questions. So, you know, each test in general is about 3 chapters, right? So you have 60 questions to work with. And again, these questions are very reflective of the chapter of the material. So, practice them. Hopefully, you're telling your friends about them if they're taking these practices or watching these videos, right? And also, you can always twist these questions around. Like, if it's asking for something, what would it be if it asked for the opposite thing, right? So, twist them, manipulate them, use them to your advantage, right? Pick at them, things like that. So, with that being said, first, pause the video. Feel free. Take your time, write notes, um, try to answer them, and then we'll go through them. Okay. So first, you should have gone C. So what is the first step in general mechanism of electrophilic aromatic substitution? C, um, addition of the electrophile to the aromatic ring, right? And actually, now this is another way you could kind of test yourself, right? What's the second step, or how many steps are there, right? So first step is that electrophilic addition, right? Electrophilic addition, okay. Addition. And then second step is what? The deprotonation, right? So we know every time we add something, and this is where what I was telling you guys about, the basics kind of, as long as you know the basics, you kind of know what's going to happen next. In addition, we know a pi bond leaves, and then it's going to end up with a carbocation, right? So um, that's where the deprotonation comes in, right? Deprotonate that carbocation out. So things like that. And for these are always the first step, well, the only steps for electrophilic aromatic substitution. So that's all you need to do. And why is it an addition instead of substitution? Well, in this case, because of that second step, it is kind of like a substitution, right? So don't get tricked by that. Two, you guys should have gone B. Why is sulfuric acid in aromatic used in aromatic nitration? So for this, you just have to know the reaction, right? Obviously, the reaction is nitration, and we know nitration affords what product? NO2. So that's all they're asking. You didn't have to know, the specifics. We know nitration uses, let's see, HNO3 and H2SO4, right? So this is our sulfuric acid, and this is just another way of asking this question. Um, but we just needed to know that it makes NO2 plus, right? Which is B. Now 3, you guys should have gone. Let's see, which of the following halides will not work in Friedel-Crafts? Is A. Friedel-Crafts alkylation does not work on what? And this goes back to either OChem 1 or earlier. Um, I'm thinking OChem 1, but we've definitely seen Friedel-Crafts before, so it does not work on which kinds? On either aryl or vinyl halides, right? So aryl halides, something like this, or vinyl, right? Something like this. So they don't work on any of these. Does not work. So that's all with Friedel-Crafts, right? And that's it. It reacts with everything else. Okay. So now let's go to 4. And this one is a good question. Oh, actually, let's keep it consistent with the dashes, right? 4, from you should have gotten D, right? And why is that? And this doesn't only relate to the nitro group, it relates to all the directors, right? They're directors because it removes electron density from whatever group they're not directing to than the group they are directing to, right? So they deactivate, activate, things like that. Um, so in this case, directors deactivate the position they're directing to less, right? So you could have asked, why is the alkyl group a ortho-para director? Because it's deactivating the ortho-para position less, right? So things like that. 5, which of the following statements about the mechanism of EAS is not true? So this one is also a good concept question, and you should have gone B because the transition state is going to be higher in energy for the first step. So for EAS, it's gonna look like this, right? So it occurs in 2 steps, right? We have 2 steps here. B, the first step is higher in energy. The first step is the rate determining step because it's the higher in energy, right? Rate determining equals higher EA, right? Higher activation energy is always the rate determining, and that doesn't just what's it called relate to this specific one, but it relates to everything, right? And let's see, the second step is a fast step, which it is because it has lower activation energy, right? So that's that. So that's it for those first 5. So now let's go to the next page. Okay. So pause the video, gather your thoughts, um, work them out, and again, reactions, right? So no biggie. And let's see what you guys got. And again, I know you guys, for some of you that have your reactions down, these are probably like whatever questions, But again, knowing the types of questions, just being familiar with it, and you guys are probably already are because you guys have gone through OCHEM 1 and then you're pretty much halfway through OCHEM 2, right? You guys are probably used to this, but practice is good, always good, and it's free. Um, so, and you can always fast forward to the good parts, right? So, but hopefully you guys still watch, you know, the not so good. Okay, so what is a major organic product? 6, you guys should have gotten D. Why? Because the methyl group. And I guess to emphasize this, for directing groups, we look at the reactants, right? So we don't care about the reagents, right? So we don't care about these, right? This is what we're looking at. So this methyl group is a what director? Ortho para director, right? So we'll either have, and this is another thing, draw them out first. What are the products? So we'll have the methyl right there, right? We keep that. And either ortho or para positions for the CL. So either here or, so we'll keep that, or here, right? So which one of those match the choices? Right, D. So things like that, always pay attention to the reactants because I know some people kind of confuse it with, oh, Cl is what we're looking at. It's like, no, you're looking at the one that's already on the aromatic. Okay, 7, you guys should have gotten B. And why B? So this reaction is just a general reaction. It's just a general addition reaction, right? So you literally just pop on to the benzene. So in this case, we have this, right? And then that OH leaves. So the OH was right here, right? So just bond them like that, right? And let's redraw it, and you just redraw it what B would look like, right? So something like that, right? So nothing too crazy. And this is where, again, this is not a specific reaction from the chapter, right? This is just us using our general knowledge of reactions. We have a benzene, we have an OH, alcohol, right? Alkyl group, things like that. So, and we just add them together. Okay, 8, you guys should have gone A. Again, this is those. Now you guys should have be familiar, very familiar with the chart. Depending on who your professor is, they might provide it to you and they might not. From my experience, they have not provided it because that's literally the whole chapter, which is the chart, right? So you just basically have to know that the activators and deactivators, which ones are the most prioritized, which ones are the most deactivating, right? Things like that, what they do, ortho meta, para, where do they go, where do they direct, things like that. So we'll look at the chart later in the summary. 9, you guys should have gone D again with the chart, right? So pretty much different ways to ask the questions about the chart. Is it ortho para meta? Is it activating, deactivating, things like that? So kind of like choose your poison at that point. Pretty much anything is fair game. They can word it any way they want. They can rank it for you, things like that. And then 10. Hopefully I have room here. 10. What is the following reaction? NHCOCH3. So again, we're looking at that. What kind of director is NHCOCH3? We find that it's a orthometa. So again, pretty much the same as the methyl group back in number 6. So you guys should have gotten D. So again, just kind of, let's draw it out. And NHCOCH3. And the thing is, also, just because we know it's orthopara, don't forget about the product that you're making, right? We're making, this is a nitration. So we're making NO2, right? So don't forget that. And that'll be D, 1 and 3, right? So orthopara positions. Okay, so now let's move on to the next page. Kind of going pretty fast, right? Because it's just reactions. And yeah, that's good. That's good, I guess. Okay, so again, pause the video. Um, you know, take your time, get your answers, and see what you guys come up with. Okay, so for 11, you guys should have gotten B. And again, this is where you have to know the chart, which one's more, um, activating, deactivating, things like that. So we said 2 is the least, and over 1 and over 4. Okay, I don't know why I'm rewriting this, but okay, I'm 2 in it. Okay, so the best thing here is knowing that benzene here is not an activator or deactivator. So I like to call it just the standard. It's standard. It's a 0. It's nothing. So either you're deactivating below it or activating above it, right? So the halogen is a deactivator, so it's below benzene. The rest are activators, so it's above benzene, right? So I like to call benzene the standard, right? Standard, like it doesn't do anything, it's 0. Um, so nothing really crazy with benzene. Now 12, what are the products of the following reaction? This one, again, OH is a what? OP director, so you guys should have gotten D, right? And this one is interesting because now it says it's only D. We know it's orthopara, but these are one of the few exceptions, right? It's called polyhalogenation. So pretty much all activators can polyhalogenate. Yeah, that's pretty much it. Um, activators, and none of the deactivators polyhalogenate. So that's all there's to it with polyhalogenation. Nothing too crazy. Pretty much if you see OH or NH2 and any of the derivatives, so um, let's see, OH, NH2, and derivatives, so like OR, things like that, or NHR, NR2, all of those can polyhalogenate. Now, if they say, for instance, there's only one equivalent of Cl2, then obviously it's just going to be one Cl added, right? But in this case, we're expecting the excess because they didn't mention it's one equivalent, right? So for 13, so this is kind of not related, but kind of, you know, the same type of concept with the polys, right? Polyhalogenation, polyalkylation. So we know polyalkylation, obviously, multiple alkyl groups added. So kind of just like number 12, but instead of halogens, it's alkyl groups, and this is Friedel Crafts. So you guys should have gone with B, and this one makes sense. So first, we can get rid of C and D because Friedel Crafts does not deal with acids or bases or anything like that. Um, okay, so now let's think about this. So pretty much A and B are flip-flopped, right? Excess alkyl halides or excess benzene. So we know how do Friedel Crafts work. We start with our ring, right? so Frito Craft, and then we um, use alkyl halides to um, alkyl alkylate it, right? Alkylation. So RC, or I guess RX, right? RX, and what, AlCl3, right? That type of thing. So how can polyalkylation be minimized? So if we have more of this, right, then it's more likely that they'll go pretty much not going to be an excess because there's more of the reaction, that type thing. So there's not really a specific like rule to this. It's just kind of like common sense. If we have more of this than this, obviously it won't alkylate one thing because there's everything else that needs to be alkylated first, right? So think of it as everything has to be reacted first before you can go for second round, right? That type of thing. So in this case, if you have more of this, there's no second rounds. There's no polys, right? Polyalkylation. Okay. Yeah, that one is always an interesting one. Okay. 14. Again, you know, stop yourself, stop myself, pause, and let's see what you guys get. So, 14, you guys should on D. And again, this one is a good one because now we're dealing with what happens if there's two things, right? So we know OH and methyl groups, both OP directors. But who do we follow? Because this OP, this methyl's OP is different from this OH's OP, right? So prioritize um, best activator, right? So we know OPs are activators, so we're gonna go with OH because it's the more prioritized activator. So in this case, we'll go with either the ortho, right, or para in relative to OH. So that will leave us with 1 and 2. Um, yeah, and again, nitration again, so NO2, right? Okay, so 15. I feel like these lights are brighter than usual today. Okay. Which of the following statements about nucleophilic aromatic substitution is not true? So now, we've been dealing with electrophilic aromatic substitution, but there's also nucleophilic aromatic substitution, which is pretty much opposite of electrophilic aromatic substitution. So in this case, you guys should have gotten D because um, when a nitrogen group is located in matter to the halogen, the negative charge of the intermediate carbocation will be delocalized. And just from reading that, like we don't even need to know what nucleophilic aromatic substitution is, right? So let's see. We have here a nitro group, so NO2 is located matter to the halogen, right? X. Um, the negative charge. So basically, they're saying if this happens, right, the carb anion, if this happens, the carb anion can be localized onto the NO2 group, thus stabilizing it. So can this end up all the way over here to stabilize it? No, right? Because this is talking about rearrangement, things like that. And even still, there's no way for it to go all the way up here since there's just too much space, right? So even if we, let's see, let's draw it this way, right? Where can this jump to without causing the aromatic to separate, right? So even if we move this over here, where is this pi going to go? right? So it's really iffy. It's just doesn't make sense. And let's look at the other ones. Increasing the electronegativity of the halogen increases the reactivity. That's true because that's what nucleophilic aromatic substitution is all about. Um, electronegativity. B, increasing the number of electron withdrawing groups increases reactivity. Yes, so pretty much A and B are pretty much the same thing. C, electron withdrawing groups stabilize the intermediate and lower the energy of the transition state. So that's also true because again, electron withdrawing groups kind of, um, you know, take off the energy from something, right, from another atom. So okay, let me erase this and we'll go to 16, 17. 16, rank the following in increasing reactivity in nucleophilic aromatic substitution. So we're still in nucleophilic aromatic substitution, and with nucleophilic aromatic substitution, okay, we know we care about more electron withdrawing groups. So in this case, you guys should have gotten B, right? So the most electron withdrawing group or the best electron withdrawing groups are more reactive. So in this case, one for sure is out, right? Two and three, we know fluorine is more electronegative than Cl, so that's why three is the most reactive. 17, so I guess best electron withdrawing groups, reactive, really, right? So 17, which air fluoride reacts or passes with NaOH? Um, same thing. This one, again, the best electron withdrawing groups win, right? So 17, you guys should have gotten C, right? So nothing too crazy. Um, yeah, pretty much nucleophilic aromatic substitution just cares about electron withdrawing groups, right? So, right. Okay. So now let's go to a new page. Last page. Again, pause the video, do what you want, do what you will, screenshot, you know. Okay. Which, sorry, which set of reagents most likely bring out the following transformation? So now, again, you can find the reactants, you can find the reagents, you can find the products, so any which way about reactions, right? So you guys know that by now. 18, which of the reagents would most likely bring the following reaction? So why is it B and not the rest? So this um, question deals with the halogenation of allele benzene, right? So allele benzene. So with allele benzene, um, the only way to add a halogen to allele benzene is with the NVS and light because all the other ones will go to um, the Markovnikov, right? All the other ones will go into this product, right? Because of Markovnikov. So NVS and light is the only one that attaches to the allele, right? And this is the keyword allele part of the benzene. Okay, so 19, best choice reagent to bring the following transformation. So now you know what's going on. What's going on here? We got rid of the carbonyl. So what kind of reaction is that? Is that elimination? No, it's not elimination. So because why? Not elimination because no pi bonds were made, right? So 19, you guys should have gone B, and there's two reactions here that you could have used. B is the Clemenson. You guys could all have used as well, or Wolf Kushner, right? Wolf Kitchener. Both of these are um, reduces the reduction, right? So they reduce and it did get reduced, right? Okay, so 20, what is the product of the following reaction? FeHCl. You guys should have gotten this one, B. Why B? Because this reaction is reduction of nitrobenzenes. So we just care about the nitro, right? Um, we're not adding anything. We're not adding halogens at all. So as you can tell, um, a lot of different reactions, and a lot of them are pretty. Some of them are straightforward. Some of them are kind of like, you kind of have to get used to because it's either been a while or it's just completely new. Um, so as you can see, they're mostly reactions, right? So with that being said, let's see what these reactions are. Let's list them, right? Listing the reactions is probably our best bet. So let me remove this. Oop, and let's get started. So first things first, electrophilic aromatic substitution, or EAS, right? So again, with this, keeps aromatic intact. We don't want to break it. And the first line, or the first step, is always what? Addition of electrophile, right? Addition of electrophile, then to deprotonation, right? Nothing too crazy with base, right? Nothing too crazy. And again, since I'll go to another page anyway, I'll just add this, right? This is what the steps look like, right? I drew it better earlier, but so this is the first step, right? Slow, rate determining. Second step, right? First, second, slow, rate determining, determining, fast, right? So that's what you're looking for. So now let's go to the specifics, and I'm just going to abbreviate EAS, electrophilic aromatic substitution, AS. Okay. So first off, we have halogenation. As always, we always have halogenation, right? So here, and I'll draw the H here. We have X2, FEX3, right? Don't be alarmed for the FEX3. It's just going to add 1, right? 2, nitration. We saw this a lot earlier. Again, let's start off with H. We have HNO3, H2SO4, right? And we're just adding NO2, NO2. And then you'll see later that we can even go further down with this to NH2. 3, sulfonation. So pretty much the same as nitration. We don't see this a lot, but it's there. Okay. SO3, H2SO4 again. SO3H. Right. Now we have Friedel Crafts. Oh, I hope I have room. Calculation, right? H. Let's see. I think I have room. RCL. And this one we do the R group, right? We get the R group. And this one, not on vinyl aryl halides, right? That's the important thing about Friedel Crafts calculation. So last one, Friedel Crafts acylation. Yeah, and there's a difference, right? This one makes carbonyls. So this one, you start off with, again, just a plain one, and then RCOCl, and the same AlCl3, right? And then you have the acyl group, right, which is the RCO, and that's that. So these are your general electrophilic aromatic substitution, right? Okay. Now, again, what affects these reactions? So, same thing as what affects other reactions, right? We have inductive effects. Inductive effects, so that means like electron withdrawing groups or electron donating groups, right? So resonance effects, resonance is always in the back of your heads, right? Especially with these aromatics, obviously, you're gonna have to keep an eye on that. So again, resonance, if you have pi bonds, lone pairs, things like that, charges. We have substituent effects. So it can affect the rate and the orientation. Reaction or the position. So ortho, meta, para, right? And then here we have directors, which is pretty much the same, right? Directors, so, pretty much the only kind of real note here is that, again, if there's multiple directors, more powerful activator wins, right? And pretty much here, no substitution between two meta positions, right? And you'll see later, and you'll kind of see why, because it's just because of crowding, right? So that's it. And also, I guess the last one here, benzene derivatives. So pretty much you can, again, this is pretty much all the reactions we listed earlier, right? All the benzene derivatives, um, which in turn make into substituent effects on the directors, right? The nitro groups, oxygens, alcohols, methyl groups, things like that. Okay, so that's that. And now, the fun part, we're going to the directors, right? The directing effect. So hopefully this fits on this. But, so basically, let me list them for you. NH. Actually, let me tackle it. Reactivity. and directors. So bear with me. Or fast forward to when I have it done. Okay. And this should be in your books or in the PowerPoints you're using. Um, Definitely you should memorize this. Okay. Oh my god, I don't even think we have enough room. Okay. NHCOR benzene. CHO. Okay, I'm not gonna have room. But RCOOHCN, right? So on and so forth. Actually, let me do this. Since pretty much these are, once you get here, there's nothing special about them. So I'll add them to here and just know that this is um they get lower and lower, right? SO3H, NO2, and R3, right? So they get lower and lower. Now let's do some colors. So let's do blue. These are all activators, right? And you can kind of tell most of them have lone pairs, right? So that's kind of like their um, defining factor. And let's do red. So obviously are the activators. And you can see how most of them are positive, um, partial to fully positive, right? Partial to fully positive. So that's kind of take away. And again, like I said earlier, right? This is kind of the standard, right? The benzene. It's kind of our standard. And now there's another kind of separation is, I'm going to do this. These are going to be, and this is up to the halogen, right? And this is up to the R group, by the way. Okay. So with this, these are your orthopara directors, right? And they're also the electron donating group, right? And now this is where the polyhalogenation stuff is. They polyhalogenate, but this one, NH2 and derivative, derivatives do not undergo Friedel-Crafts calculation. So there you go, right? And you can kind of see how these are electron donating groups because they all have the spare lone pairs, right? So now let's go to the next one. Let's do this. Actually, no, let's do yellow. So this was just pretty much everything else. right? And these are your meta directors and electron withdrawing groups. And all of these, no cradlecrafts at all, right? No cradlecrafts accumulation as well. So that's kind of like, I guess, you know, why. It's because of their, um, it's because of their composure. It's because of the group. Um, Cradlecraft deals with um, what the alkyl groups, right? And these just don't have that. And you can see that our group here is over here. So kind of things kind of like that. So this is kind of a bit messy, but again, kind of redo them. But all the information here are good, especially all these random ones are good. So yeah. So this is what I have. I don't know if you can kind of see, but this is what I have. So do them with do colors, things like that. But yeah, definitely memorize this, and it will help you. And again, you know, not just knowing what one is, right? What's an activator, deactivator. You kind of know. You need to know the rankings, right? And again, this is the lowest one up to here, and then go up, and then so on and so forth. So there's that. Hopefully that made sense. Okay. Now let's go to nucleophilic aromatic substitution. So NAS. So this one, the most important is the reactivity. So reactivity increases as electron withdrawing groups increases. Reactivity, right? And again with electronegativity, which is pretty much the same thing, increases reactivity. So with this, an important little tidbit, kind of like why that happens, it's because it stabilizes stabilizes carb anion intermediate, right? Which makes sense because carb anion negatively charged, so you want to take away that negative charge away from it, so it's not so reactive, right? So it's not so, I guess, unstable, things like that. So with this, NAS only with aryl halides with OP directors, right? So that these only happen NAS, nucleophilic aromatic substitution, only with aryl halides with OP directors, right? So another little thing here is that there's two kinds. There's an elimination addition. There's addition elimination. So addition elimination first, and we have elimination addition. So with elimination addition, or I guess let's do this one first. The steps are kind of like flip-flopped, or not flip-flopped, but different. So addition of nucleophile, right? So here it's resonance stabilized, resonance stabilized, um, like usual. And then you have your loss of X. So elimination, right? We add the nucleophile, lose the X. So here we have elimination first. So this is going to be, when you eliminate something, again, you make a pi bond, right? So you're going to end up with a benzyne. So a triple bonded in a benzyne, a triple bond in a benzyne, right? So super reactive. Um, so the second step is just addition, right? Addition, protonation to kind of take off that um, triple bond, right? So that's kind of the two ways to do that. So if once you start hearing benzyne, that's definitely nucleophilic aromatic substitution, right? So benzyne, it happens. Okay, so now let's talk about miscellaneous reactions. So there's a couple, and these are probably towards the end when we're doing our review, towards the end of the question. So first things first, we have the reduction of aryl benzenes. So we have the Clementon, right? And we have the Wolff-Kishner. Kishner. So Clementon, we saw that earlier. We deal with zinc, mercury, plus strong acids. With Wolff-Kishner, we deal with, this is pretty memorable, NH2, NH2. So that's good. Plus strong base. So one deals with strong acids, one deals with strong base, right? So both use heat and cleave COO, right? And we saw that happen. We just cleave it off. Two, we have synthesis of alkyl benzenes. So this one is just both the Friedel crafts, right? So Friedel crafts, we saw that. That's it, right? Friedel crafts. A third one, reduction of nitrobenzenes. We saw that in the question. And basically, we can make nitrobenzenes, right, from the first set of reactions we did earlier, but now we can reduce that into an aniline. So pretty much, let me see, nitro group, right, to NH2. NH2 right there. Oh, right, and this one we use either, there's a couple of reagents we can use, H2 PDC or FeHCl or SnHCl. Right, so a lot of different choices to reduce that nitro into an aniline. Okay, so now there's more. Reactions. So now we have a couple more. So we have halogenation. And a lot of these names are kind of like, yeah, we know what halogenation means, right? Halogenation of alkyl benzene. So in this one, we have an alkyl benzene, a halogenation. Let's start off with this, right? And then we either have Br2 with HV and heat, right? Or NBS, right? What we talked about earlier with HV or heat. and there's our Br right there. So it goes to the you know, this carbon again, right? So this was halogenation, and that's because of the heat, and that's because of the um, you know, wavelengths, things like that, or radiation, HV. Okay, 5 we have okay, ionic and radical halogenation. Okay, so for this one, um, you just halogen it again, but this time ions and radicals. And we've seen this before. It's just halogenation again with ions. So let's start off with the same thing we did on number 4. So we have this, right? And this is where the difference comes in. Over here, and then we have another one over here. This one is the just the Br2Fe Br3, and this one's the Br2 and HV heat. So like this, like the fourth one. Actually, I could have combined them, but oh well, too late. So this one, I'll put the Br over here in the bottom. So you notice here, this is the ortho position, right? And this is the para position. But this one, it added onto here. So now you kind of see what the ionic radical halogenation was different. We know this is an orthopara director, right? So this is kind of with just a regular halogenation, it goes to the orthopara. But now when you're dealing with heat, things like that, it still goes to that allyl carbon, right? Okay, now last one, I ran out of space, but last one, MISC reactions. So 6 oxidation of we had reduction, right? Now we have oxidation of alkylbenzenes. So it must at least have one benzylic hydrogen, right? And affects all alkyl groups, and you just use KMnO4. So benzylic H is the hydrogen, right? The hydrogen on the adjacent carbon from the benzene. So there's H here. So obviously, if you have a let's say a tert butyl, right? There's no H here, so this can't react. So no reaction, right? But this one's good. So benzylic hydrogen is the important one for oxidation, and for that you just oxidize it. You just add a double bond or an oxygen, right? So in this case, a double bond because it's KMnO4, right? Okay. So with that being said, that's all I have for you guys. Hopefully it helped. Um, the review, hopefully that should have helped greatly. Hopefully, um, lots of reactions. This is probably the most reaction we've had so far for one chapter. Um, but again, it's kind of you kind of see how they kind of stack up, how they get kind of a little bit repetitive, and how you kind of tell ahead of time or kind of deduce how to do them, even though you don't exactly know how, you know. And there's not a lot where it's tricky, where um, the reagents are mixed up or complicated, I guess. But for the mixed reactions, as we wrote, those are important because those are often the ones that get forgotten. So don't forget about those. Okay, so guests for joining me today, and hope to see you guys next time. Bye.